Okay, thank you. Right. So it's very nice that we have the chance here to speak in such a big audience, and also good that we have more time, and thus we decided to have this presentation together. Yeah. So this is Leo, my colleague, and I'm Philipp Hagedorn from the Chair of Computing and Engineering at the Ruhr University Bochum in Germany. And today we're going to present something about definition of a container-based machine-readable IDM, integrating level of information needs. And this paper is, so the idea for this paper was based on both of our PhD researches, which are about information exchange, in my case more in the design and construction part, and in Leo's case in the operation phase of assets. And therefore we first looked into the general information delivery process as it is also defined by Building Smart and others. Which usually starts with someone defining requirements, what has to be done, what has to be exchanged, then awaiting kind of provision by other stakeholders that are part of the project, and they deliver the required information, going over to the approval of information, which can contain some kind of requirements checking process, and finally the sharing with the whole project consortium, or all the stakeholders. When we now look into how this process is done with BIM or in BIM-based projects, then we have the requirements definition using IDS, which is quite a new thing that is currently developed by Building Smart. Therein all the requirements for an IFC model that has to be produced by the BIM authors or whoever are specified. Then in the next step we have the provision of the IFC file, and based on the IDS we can check whether the requirements are met that were defined in the first place. The sharing process is usually done using common data environments where all the stakeholders then have access to. However, usually we don't just exchange IFC model, but also a bunch of different other heterogeneous data like PDF files, like images, whatsoever. As we already have heard in Anne's presentation, there's a lot that is transported within a data exchange maybe. And therefore, which is also pretty much my PhD research topic, we looked into information containers, and therefore specifically in the information container for linked document delivery, abbreviated ICDD, which also Anna just mentioned in her presentation. And then we looked how this process that is pretty much clear for exchanging IFC data is done when we have this information container. So basically the provision now is done with the structure that the information container defines. And also we can state that from the standardization part, common data environments are capable of using information containers for sharing information between project participants. However, more or less two things are missing in this row here, in this process. This is on the one hand the requirements definition for this whole container, not only the IFC file, but all the documents that are delivered. And concludingly also the checking or the approval of these requirements. Which leads us to the research question, how can machine-readable exchange information requirements for ICDD containers be defined? Therefore, we first look into what is exactly this ICDD container, and we can see the structure of this container on the right-hand side. This container is standardized in ISO 21597, and it's specifically exchange specification for overcoming the lack of vendor-neutral structures, exchanging both heterogeneous and also distributed building data. And this container allows linking on the entity level, so we can also establish deep linking here, and is encoded in semantic web formats, which means we use RDF and the ontologies that are provided by the standard to link everything together in this container and also enrich the data with metadata descriptions. When we look at information requirement specification generally, then we have information requirements as a request for explicit information that are delivered in a project, in a BIM project, which is also part of the information delivery manual. And we have seen that there are multiple ways to encode these requirements, which is pretty much depending on which tools you use or which formats you use. And therein, last year at the ECCPM conference, there was this work by Artur Tomczak and others that had a deeper look into all the possibilities how to define information requirements in BIM projects. And one output of their research was this table that you can see here. And we took this table to see how or which parts of this we can grab and put into requirements for this information container. And there we basically saw that IDS is very capable for IFC files, but also LOIN and this linked data and shackle part are very interesting, since also the container is based on RDF and linked data. So the level of information need, short LOIN, is also an international standard that encompasses the description of required geometry, semantics, but also the documentation or documents. And thus we considered it as very suitable also to describe the contents of information containers. Next we have the IDS, which is then very capable of addressing requirements for IFC files. And the linked data part, I already said, fits very good to what we have with the information container. But also we have seen that shackle is a very, shapes constrained language is a very powerful tool for validating RDF data. And also a lot of other sources from this linked data field, like the semantic building smart data dictionary, can be incorporated then into the requirements specification process. So when we sum this all together, we try to superimpose the approaches in the original table by Tomczak and others, and have seen that this could be quite a good coverage of different aspects. So there's no claim for completeness in this table, but just as superimposing them, we thought this might work. Thus, our objective for the paper was to develop an ontology that combines the level of information need and IDS and ICDD for the requirements specification. We had the following methodology. First, what I also just presented was gathering the purpose, the scope, functional requirements as it is depicted in the linked open terms methodology, which is a common methodology for developing ontologies provided by the Ontology Engineering Group in Madrid. So we started with this, thinking about use case, purpose, and scope, identified the research gap from the current literature, and came across the LOIN standard here. Then when it came to the ontology implementation step, we started with providing a vocabulary for the LOIN ontology first, extracted from the standard here, and then extend this vocabulary with first the IDS terminology that is also currently under development, and connecting this all to ICDD. Finally, we put this all together in a use case or demo scenario for the ontology evaluation, where we had kind of use case also from the operation phase based on pavement management, which also will Leo present in the second part of the presentation. Okay, and now I give over to my colleague.
Thank you. So I continue with the ontology development and evaluation and try to give you a deeper look into the development steps and the ontology structure. So the development of the ontology started with the encoding of the standard level of information need, abbreviated with LOIN. This standard provides a concept and methods for describing information which is required and also should be exchanged by the information delivery process. The LOIN standard, definition is considering the standard ISO standard 19615 part 1 for information management using BIM, and the information delivery manual IDM standard. To describe the correct level of required information for exchanging, the LOIN contains two part terms for the information delivery. The first part contains contextual aspect of information. It provides how can give the still laser point? Okay. So the contextual, the first part contains the contextual aspect of information. It provides the answer to the question why and when should which information be exchanged by whom. And the second part of the definition of the concrete information need is for the definition of the concrete information need, in which the geometrical, alphanumerical information and the related document can be specified. So based on the LOIN, the ontology classes are defined to reflect the main concept of this standard. The contextual terms are defined with 4 classes, like information delivery manual, object, purpose, and actors. The 3 aspects for defining the information need, here the geometry information, are associated with a to be exchanged object using the object property has geometry, has information, and has document. For the geometrical information, there are 5 standardized specifications like detail, dimensionality, and location, and so on. These are defined as subclass of the geometric specification. Compared with the geometric information, the standard provides a simple generic manner for defining the alphanumeric information. It contains identification for positioning one object in a breakdown structure, and also the information content for the required properties. This generic concept can be ideally used to extend with detailed specification. And the third part, the documentation is defined as a class which can contain various documents using the object property has document. So after this step, we can say that for the terms of the alphanumerical information is very simple. But this kind of information is most important for a precise description of building and structure status, and also mostly required by a data exchange. So the current development of building smart address these issues and provide the information delivery. So information delivery specification for specifying and checking the exchange information requirements for IFC model. The original IDS is encoded with XML, and the file format is defined as .ids. The exchange requirement declared in IDS content declared in IDS contains three major parts. First, a description for human understanding with explanation of why the information is required, and then the applicability for specifying the IFC entities or classes to which the information requirements should be applied. And the third one is the specification of the requirement itself. So this example defines actually a very simple requirement for the entities belonging to IFC DOR, and they need to have a width in value between 0.9 to 1.2 meters. Furthermore, to specify the applicability and requirement, facets need to be used. So there are facets need to be used, and to reach the information requirement. Sorry, I'm start with the facet. Facet need to be used, and there are 6 facets like entity, attribute, and properties that's defined in the IDS, giving the detailed approach for the declaring the exchange information requirement by IDS. The extension of the ontology integrates the IDS terminology into the alphanumerical information. And in this slide shows that the blue-colored terms are the extension of the classes and properties considering the IDS. And IDS specification can be defined using the class IDS data definition. With the data type property description of this class, the reason for the required information can be explained with plain text for human understanding. The applicability and requirement can be defined using the IDS facet definition. With the object property has applicability and has requirement, a facet instances can be declared whether it should be applied with a requirement or it is a requirement definition. So related to the facet definition, different parameters are used to specify the information of each facet instances. The parameters are modeled in the associated ontology classes and as subclass of the IDS facet parameter. In addition, the restriction type class for the parameter can declare if a parameter formulation is a simple value or using a complex restriction pattern. And the class IDS requirement type is used to specify if a requirement is optional or mandatory. Considering the main idea of IDS, define one information exchange for one clear purpose with clear responsibility. The information from the contextual aspect are also defined with strict relations with extended object properties and the restriction. So as a last step of the ontology development, we will attend the connection to the ontology with the ICDD terminology. So as we already mentioned at the beginning, of the presentation, comprehensive data can be delivered in form of different documents for one exchange process. Therefore, information container is more feasible for data exchange through different phases of the construction life cycle. For the information container, the ISO standard provides the container ontology and link set ontology for defining the container. Using this ontology, container can be described and the document can be added into the container with simple meta information like name and format. But the connection between the container content and the exchange information requirement is still missing at this moment. So we make the extension of the extension of the component of contextual alphanumerical information and documentation for the alignment with the container ontology. The right-colored classes are defined at first for clarify of document instances that has user class LOIN document. For example, the document purpose can specify if a document just provides information or existing information or should be used as a template and be delivered later. The content can specify the document in a wide range from the technical report, damage in photos, to the 3D object models. The class document format is intended to clarify the document file type, such as IFC, PNG, or PDF. The object property is related to LOIN document, make a better connection between the defined required, the required information and the defined LOIN documentation. To describe the container, the LOIN, the instances of information delivery milestone and the purpose can be linked to the container description using the object property is related to container description. And the same way is also for the actor defined in the using the LOIN ontology to the container class party. With the extended object properties is related to container link site or is related to container document. We can specify the container content, document, and link site through the defined document and the specification. So now the ontology is able to define the alphanumerical information in a detailed level and also aligns this with the information container. So at this step, we have defined 3 sub-processes to prepare the exchange information requirement. The 3 steps I would like to introduce combined with the use case pavement inspection. So for our general pavement inspection, we limited 4 properties which value are required to for assessing the pavement condition. To perform the inspection, a spillage model is available for the contractor, which contains existing information about the pavement session. And to deliver the required information in a correct form, another document inspection layer is also provided by clients that should be used as template and completed with the required information by the contractor. So all this information all this information are defined in the LOIN standard, using the LOIN ontology as a first step. As a second step, we create the documents which are already specified in the LOIN instances. And in this case, as built information, as built model and the IFC road section, the two IFC model are created. Okay. And now in the last step, the information container can be created using the ICDD platform. The defined exchange requirement using LOIN ontology and the two IFC models are added into the container. A container link site is created to link the LOIN document and the LOIN document specification with the IFC model in the container. Now the container can be handed over to the contractor for the pavement inspection. So within the information container, different relevant information can be about the exchange requirement can be retrieved through the Spark query, the query language for RDF-based information. For example, there is a query prepared for user if he would like to get an overview of the purpose and content from the available documents in the container. The requirements result shows the real documents in the ICDD container and the document specification about format, content, and purpose, which are defined using the LOIN ontology. Another example shows which information should be delivered by the contractor in relation to the real document in the ICDD. The query result shows 4 properties are required and should be applied to IFC building element proxy using the IFC model road inspection session. So now I'm finished with the evaluation and would like to give back to Philipp for the conclusion.
Okay, so concludingly, what have we done and what have we achieved with our publication? First of all, we've seen that a lot of building data nowadays, especially in research, is either modeled or described using semantic web technologies. And so we said definitely we also need the requirements to be in linked data and semantic web, because otherwise makes no sense. But from that on, we now developed this LOIN ontology, and this LOIN ontology, as we just have seen, provides added value, especially working with the ICDD container, because now it is all integrated. So we can now also check the requirements of the container and prove that the contents are actually delivered. The extension of the LOIN ontology with terminology from both IDS and ICDD was very helpful, because we have this interrelation between the process on the one hand and the data on the other hand, so that we overall get better data integrity and validity. And also this machine-readable information requirements that we are now able to specify are kind of the foundation for the automatic shackle validation of ICD containers, which is also part of our future work, because this whole shackle checking is still something we are right now working on, and also the duality between IDS as an XML and IDS, which we provide in the LOIN ontology. We're also working on this to provide conversion either way, for have directly the model checking but still maintain the IDS also in the overall exchange information requirement. So finally, we have the documentation and every resources online on GitHub. This QR code is a little bit off here, but your participation also in this is very welcome, and if there are any comments on the ontology or any suggestions, there's also the issue tracking at GitHub, so or you can also reach out to us here at the conference, which would be maybe also easier, but you can find all the resources here. And yeah, that's it from our side. Thanks for your attention, and we are happy to answer questions that may arise.